So we're going to talk about the phase of a wave. Two waves are considered in phase if they are at the same point in their oscillation at the same point in time. So they might look the same, and what we want to look at is that they actually have the same form at the same time. Why is this important? Well, what happens when they're out of phase, when they're at different points at the same point in time? So difference in phase are normally expressed as an angle or as a multiple of wavelengths. So we might say that they're half a wavelength out of phase, or pi radians, or 180 degrees. And that means that basically in one case you have a sine wave, in the other you can have a cos wave. Or you can see that these now are completely out of phase. Well, when waves overlap, they interfere with each other. That is, they add up together to produce a new wave. And this is a phenomenon called superposition. When we add them together, the simple way to do it is just to basically add them up. Kind of like adding up vectors, but in this case we're actually adding up every single point on the wave to another wave. So when you add peak to peak, the result is constructive interference. But when you add peak to trough, then the result of the wave is either a small amplitude or completely zero amplitude, and this is destructive interference. So to give you an example, here's two waves which are in phase, which means that same position at the same time. How do they add up? Well, let's look. 1 plus 2, add them up, we get double the amplitude, same frequency. And this is called constructive interference. What about if they're out of phase? So two waves that are antiphase or out of phase, how do they add up? Well, add them up in this way and there's no wave left. This is called completely destructive interference. So the principle of superposition is basically that you can take any two waves and add them up, and you'll get a resulting wave. So if two or more of these waves are moving through a medium, then the result of wave displacement at any point is the algebraic sum of the individual displacements. So that's the principle of superposition. So any two waves, one's got a large, well, they've got the same amplitude, but one has a lower frequency than the other one. So this one's got a much higher frequency. What happens? Add them up and you get something that looks a little bit different. So at some points you've got constructive interference, and some points you've got destructive interference, and your new wave shape is completely different. So the combination of these separate waves is called interference, and you can see it in two dimensions when you look at the ripple tank. So these 2 points down here are the dippers, which if you dip them into the water at a particular frequency, you generate a wave, and so the wave travels outwards at a certain rate, and if you've got two dippers, then they interfere. And you can see some interesting things in this ripple tank, which we will do in class, but we can have a look here. You can see that there is interference, not so much out of here, that's kind of like the same waves as what was generated, but here you can see there is interference, and sometimes there's constructive, but sometimes there's destructive, and you see these lines, patterns that are radiating out. So what do we need for a permanent interference pattern? We have to have coherent sources, so they have to be in phase with each other, and they must maintain a constant phase relationship. And they must have the same wavelengths and similar amplitudes, and have a same plane of polarization. We're not going to talk too much about polarization, but this is what happens for a permanent interference pattern. And we'll get on to this a little bit more when we talk again about standing waves. So let's look at two sources. This is again similar to the ripple tank, but we're actually looking at it in terms of these wave fronts. So all the points on the wavefront are in phase with one another. So when they interfere constructively, then we get antinodal lines. So this is here. Remember that antinode is a maximum. And you get a whole range of them. We saw that in the ripple tank. But you can also get nodal lines where destructive interference occurs. And if you can see, that's in this point here, hopefully, which kind of works, which is out of phase. So you see it's between those antinodes, you'll have a node where you get destructive interference. And because of that, you get a range of wave intensity. And these are called fringes. And this happens in ripple tanks, in waves, mechanical waves, but also happens with light waves. So the definition we have of diffraction is that it's a spreading out of waves as they encounter a barrier. So in this case, we have waves going through a small source and they hit a barrier and they spread out. And we can have mechanical waves, such as in the water tank, or light waves. And this is a diffraction of two wave sources through a single slit, I think. So it's simply an interference pattern that results from the superposition of waves. This is why we spend a lot of time doing those superposition things.